This is Sai Krishna from Department of Aeronautical Engineering, Institute of Aeronautical Engineering. Today we will be continuing our previous lecture from aerospace propulsion. Right. The second lecture is of Newton's third law of motion and spaceflight orbits. In the previous class, we have discussed regarding the history and origin of rockets and in what way they have been developed over a period of time and during the Cold Wars as well as till date. Now we will continue with the same. First, we will be understanding in what way the Newton's third law will be acting upon a rocket, right? Basically, what do you understand by third law? It suggests a simple equation of motion, right? It suggests in what way that an object or a vehicle moves with respect to the force that has been applied. Now, a rocket, in our case, is been practical device for more than 1,000 years by using in terms of in rockets, missiles, bombardments, everything. Now, Tuskegee determined the dynamics of the motion, in which he opened a way to use the rockets as something other than artillery weapons with precise accuracy. Now, he identified the rocket as a means by which humanity could explore space. And by solving the equations of motion for a rocket, Tuskegee was able to show that space travel was possible. Now, he even identified the limitations and design issues which would have been faced in realizing a practical space vehicle. And in its basic form, a rocket is a device which propels itself by emitting a jet of matter. A jet of matter can be combustion products, particularly gases. Right? Now, the momentum carried away by the jet, which results particularly in a movement force. Right? For example, if you are taking this as a rocket, right? So, if you are understanding a basic form of rocket, anything which propels itself by emitting matter out of it, right? Among this, the momentum carried away by the jet, particularly the matter, results in a force acting so as to accelerate the rocket in forward in the opposite direction of the jet, right? Let me re-clear it. If I am considering this as my rocket body and this is my exhaust jet, right? When the exhaust just is being pushed out or is getting out, then a force will be acting on the rocket in the opposite direction, right? In the opposite direction of the jet, causing a forward movement, right? Now, essential fact that has to be considered while creating or understanding a rocket is, as the rocket accelerates or over a period of time, as the rocket moves, the mass decreases. In what way? Because the exhaust jet consists of combustion products, right? The exhaust jet consists of the combustion products, and the combustion products are made or created in combustion chamber by using fuel plus oxidizer, right? Let's say you're carrying some amount of X and Y amount of fuel as well as oxidizer, and over a period of time, as you are utilizing your fuel and oxidizer, the value or the quantity that you're carrying reduces, which proportionately decreases your mass over a period of time. But in accordance with the same period of time, the rocket accelerates to its designed speed, right? To its design speed till where it has to be performed. Next. Now, if I consider the same example for any gun or a gunnery, the propulsion will be a very different concept for that. In this, all the energy of a cannonball, right? If I'm considering it as my gun, a small cannonball or particularly a small bullet with some powder and firing. right? As soon as you apply fire or ignite the gunpowder into which, what happens is, as soon as the gunpowder combusts, it releases the various amount of gases that are capped in between the region behind the cannonball. So it will be having a same criteria similar to your Newton's law, but only thing, it will be directing all the energy that is being generated by the combustion of gunpowder towards the cannonball. Now, what happens on the cannonball? The cannonball will move along the barrel of the gun by expanding the gases that are being generated behind it. So, the hot gases are produced by the explosion of gunpowder. Once it leaves the barrel, right? Once it leaves the barrel, the energy and the velocity of the cannonball begin to decrease because the air friction as well as the drag, the speed at which the cannon moves, there will be an equivalent opposite reaction due to the air that is being on earth as well as the drag generated onto the surface. It means the pullback due to the surface or the surface area of the cannonball. Now, onto this, what happens? Now, comparing the same with your rocket, which experiences a continuous propulsive force, because on a cannon, once all the gases are, gases are exploded and the expansion of the gases are done, the cannonball which moves out will move only till the point where the air, or the energy at the exit of a barrel exists. Whereas in case of rocket, there will be a continuous propulsion, means continuous combustion and expel of gases through the nozzle, which creates that continuous force. So its flight will be different with respect to cannonball. For example, another example, better to be understand. Simple projectile. You are throwing a ball, right? Based on the input energy that you give, and if there is no any constant or continuous energy addition to that system, it falls back onto the ground. Now, if there is any continuous addition of the same continuous energy of some amount of energy, it can be in form of velocity, momentum, or acceleration. What happens? The ball tend to move farther till the point its energy gets exhausted by other factors. Right? Now, this will be our rocket and this will be a simple cannonball that we have studied now. Now, Tioski was faced with the dynamics of a vehicle, particularly rocket vehicle, and the mass in which is decreasing as a jet of matter is projected rearwards. Right? Try to understand the dynamics of a rocket. Right? Tioski, in order to create the dynamics of your rocket vehicle, what happens is, if you are having liquid plus fuel, particularly propellant, let me just read on. Fuel plus oxidizer, upon their combustion here, you will be exiting the gases. Now, for initial period of time, you are having let's say it's on the stage where it's supposed to launch. You will be having certain amount of fuel and oxygen as per your calculation. Now, after a period of time, let's say for 5 seconds, right, with the rate of combustion of these fuel and oxidizer, you will be losing a small amount of fuel as well as oxidizer over a period of 5 seconds. Now, this change will gradually occur as the time progresses, right? Because the same principle you are using, particularly on Newton's third law of motion, which is action and reaction, in which action is the forward motion of your rocket, whereas your reaction is, it is vice versa. The action is your exhausting of your jet, whereas the reaction is the forward motion of the rocket, which are equal as well as opposite. Now, the accelerating force for the Newton's law is represented by F, M, and V. Now, in this, the components where F is equals to the force that is being exerted onto the rocket, and M will be your mass flow rate, and V is nothing but your effective exhaust velocity. Now, try to understand this form in terms of rocket, right? The force that is being generated by the expelling of masses through the nozzle, which is equals to a product of the mass flow rate of your fuel plus oxidizer, right? In what is the amount of material that is being sent out towards per second, and a product of your exhaust velocity, and what is the velocity at which it is exiting the vehicle, right? Mass flow rate suggests the amount of material that is passing through at particular instant, right, per second. Now, at what velocity it is passing through will be your effective exhaust velocity. Now, a product of this will give you a complete force, which is nothing but simple thrust that is being generated by a rocket vehicle. Now, the energy released by the propeller appears as a fast moving jet of matter, particularly exhaust gases, and a rocket is accelerating in opposite direction, which is a result. Now, the Newton law applied to this dynamical system, and decreasing mass can be taken into account, and using some simple differential calculus, the resultant formula which Tyorsky obtained for vehicular velocity V is V equals to V logarithmic natural log into m1 by m0, right? And now this is your rocket equation. We will be discussing this rocket equation in form of derivation under upcoming modules, but let us understand what does the Tyorsky have derived and what is its significance. Now, V is your what? Velocity of vehicle. In our case, it's a rocket. Now, VE, as previously informed, is your exhaust velocity. Now, what is this m0 by m? m0 by m is also called as your mass ratio, also denoted by R, right? Which means m0 is your initial mass and m is your mass of the rocket, right? Now, this simple formula is the basis of all rocket propulsion, where the velocity increases with time as the propellant is burned. Now, it depends on the natural algorithm of the initial to the current mass, that is, on how much the propellant has been burned per time. Now, for a fixed amount of propellant burned, it also depends on the exhaust velocity and how fast the mass is being expelled, right? Now, let us understand this. What are the effect? What are the properties? So, in order to better understand the rocket equation, so that now let's consider a rocket which is traveling from t equals to 0 second and t equals to 5 second, right? Now, in order to identify the vehicular speed or vehicular velocity in which the rocket is moving, we need to find first is the exhaust velocity. Exhaust velocity of the jet that is being expelled through the nozzle. That is an important factor to understand. And next one will be the mass or the mass ratio to Frank. Now, initial mass is always constant. It consists of your propellant mass and considering the propellant mass, it's always oxidizer plus fuel combined, as well as structural mass, which includes all the tanks, avionics, fins, any other additional axle. Now, coming to the mass of a particular instance, now this will be structural structural mass will be as usual. Additionally, you will be having a decrease propellant mass, because in order to move from 0 to 5 seconds or from 0 to 5 meter in direction of x particularly, what happens, you are supposed to expel some amount of your propellant mass or a combusted gases. Now, as the propellant mass is decreasing, what happens, you will be able to move further, so that your overall mass decreases, right, or the instantaneous mass decreases. So based on these relations, your exhaust velocity particularly, or exit velocity, and the mass at particular instance defines your velocity of your rocket, right? Now let's try to understand the graph in which it has been made. Now, in the graph shown, where the rocket velocity is plotted as a function of mass ratio, and mass ratio, as we have discussed, is this given as R. Now, in just the ratio of initial to the current mass. Now, in the most cases, the final velocity of the rocket needs to be known. Now, let us understand the graph. The graph has been plotted in terms of mass ratio and rocket velocity. Now, for every mass ratio, let's say 4, 12, 18, 16, 20, is nothing but a value of R and rocket velocity in terms of meter. We are calculating an exhaust velocity by using the same rocket equation. Now, in this, these are your exhaust velocity that can probably happen, and using the exhaust velocity, try to understand the graph. As the mass ratio increases, right, the effective exhaust velocity also increases from its initial form. Why? Because in our case, in order to increase your mass ratio, this will be decreasing, as it's inversely proportional. As the mass decreases, mass ratio increases, right? Now, as the mass ratio increases, what we are getting? We are getting the exhaust velocity of rocket more, which in turn, as it's directly proportional, in turn increases the overall velocity of the rocket, right? Now, if you can see clearly, but after a period of time, right, although it's not necessary, we can't completely increase the mass ratio till the maximum of 20, 30, 40, however we like. Because, for example, let's say any satellite, for example, Saturn V, the rocket which have taken humans to the moon, what it does, basically it is around 2000 tons with major contribution of propellant, right? Now, this major contribution over a period of time led to only have less amount of mass ratio. Now, if you come in considering for a car which is around 1500 kgs, and it can only store a value of, let's say, 40 liters of fuel. Now, in this case, in the case of car, the mass ratio would be approximately 1 point something, whereas in the case of Saturn, it will be around 4 or 8, right? And that will be dependent accordingly by the ratios that we will consider for mass as well as initial mass. Now, these all are few terms that we are supposed to know. Now, the rocket equation that shows the final speed also depends on only two numbers. First is the final mass ratio at a particular instant, what is the mass ratio, and the exhaust velocity. As discussed earlier, your mass ratio and exhaust velocity will directly impact on the velocity of the rocket that at particular instant, right? Now, it doesn't depend on the thrust, whether surprisingly not the size of the rocket or the time the rocket burns or any other parameter. It purely depends on the final mass ratio and the exhaust velocity. And in our case, if you are planning for higher exhaust velocity, which in turn produces higher velocity, as both are directly proportional. And for the much effort in the rocket design goes to increasing the exhaust velocity, right? Whenever you are designing the rockets, exhaust velocity, in order to maximize the exhaust velocity, which directly determines the rocket velocity. Now, in order for, let's say, gunpowder, the range of propellants that are used in 19th century rockets produced an exhaust velocity of 2000 meter per second, which also calls 2 kilometer per second. But the most advanced liquid fuel chemical rockets today produce at the best of 4.5 kilometer per second, right? Over a period of time, we are increasing the exhaust velocity, which in turn increases the rocket velocity. And to achieve a high rocket velocity, the mass ratio has to be large. As discussed in the previous graph, the mass ratio has to be as much large as possible and with higher exhaust velocity to give total rocket velocity. Now, the mass ratio is defined as the ratio of vehicle plus propellant mass to the vehicle mass, right? Vehicle plus propellant mass, which is nothing but your m0, and vehicular mass is m. Although the vehicular mass will be having some amount of propellant, but at the end it will not be having any propellant due to a complete burnout. Now, the rocket can travel faster than the speed of its exhaust, right? Why? Because all the action that takes place inside the rocket, where constant accelerating force is being exerted on the inner walls of the combustion chamber and inside the nozzle. So when the speed of the rocket depends on the magnitude of the exhaust velocity, it itself can be much greater. The rocket carries both its fuel and oxidizer and needs no air to operate, for example like a jet engine. Now, Ryoski calculated on how fast a rocket needs to be traveled to reach the outer space, and he realized for the rocket equation that there was a limit. Right? After a certain point, increasing the mass of fuel has diminishing effect on the velocity gain, whereas a higher mass ratio would produce a higher velocity, but with diminishing return. A velocity of 11 km per second was needed to escape the Earth's gravitational field. Now, the first thing to do was to consider the increasing the exhaust velocity. Ryoski knew that there was the matter of combustion temperature and molecular weight. So he realized liquid fuel rockets which containing pure hydrogen and oxygen could produce a considerable amount of increase in exhaust velocity in excess of 4000 meter per second. Now, continuing with us, we'll be going for orbits. Now, what do you mean by orbits? Orbits are nothing but paths around a celestial body. A celestial body can be a planet, a certain mass, or any other form. Now, the motion of the spacecraft is always moving orbits, not in the straight lines. Let's say for any Earth, this will be an orbit in which particular satellite will be moving. Particularly, moon is one of the natural satellites in which a spacecraft will not leave the Earth's gravity, and it would be more correct to say that it gives in to the Earth's gravity. It means it cope-ups, it follows along the Earth's gravity. So the motion of a spacecraft is that of a body with a certain momentum and a central gravitational field. In our case, for example, if I consider for Earth and Moon as one, Earth will be a central gravitational field along which your moon will be orbiting. Now, this moon will be having certain amount of velocity, particularly momentum, which lets it to stay in its own place along by rotating Earth. Now, the path of an aircraft can be calculated in terms of total angular momentum it has in its orbit, which is constant. Now, other ways to defining a parameter is the minimum distance of the orbit from its focus, the center of the Earth. The rocket fires and gives an certain velocity which is tangential to the gravitational field. It means parallel to the Earth's surface. The kinetic energy from the spacecraft will be half omega square, as we all know, where m is the mass and v will be the velocity in terms of kinetic energy, whereas the momentum and angular momentum will be with respect to the center of the Earth, which is mv and mrv, where r will be the distance from the center of the Earth, not from the surface. We'll come back just a second, right? Now, in order to launch a rocket, what we will do? First, we'll have two components, particularly kinetic energy in terms of half mv square and momentum in terms of mv and mrv. Let me just rewrite. Now, in this component, for any satellite to move, initially what we will be doing, we will be giving out some kinetic energy in terms of rocket velocity with respect to the rocket mass that it has. After attaining, now momentum and angular momentum will be considering the r value, which is nothing but the radius from the center of the Earth, right? With this and particular horizontal velocity that we give with respect to your rocket equation, which is log m naught by m, it moves. Now, based on this, the angular velocity will be changing. So, the angular momentum that at this particular altitude will be same, whereas due to the continuous gravitational pull of the Earth, it will be rotating in a circular or elliptical or parabolic orbits. Right? Now, the spacecraft now moves under the combined effects of the momentum as well as the attraction of gravity towards the Earth. Now, it will move in a curved path that can be represented by an equation of motion and as well as a solution. The equation of the motion will give you the r, which is radius of the orbit, and the current distance of the spacecraft from the center of the Earth as a function of the angle made by the current radius vector of the closest approach. Now, as the time elapses, the spacecraft will travel along the curve shown, initially becoming farther from the Earth, while the angle increases. The expression for the path is 1 by r equals to g mass of Earth and m square divided by h into 1 plus epsilon cos theta. This is also called orbital equation, right? This defines the total orbit in which the aircraft or spacecraft moves. Now, in this expression, g, which is a constant value, is also called as a gravitational constant, which takes place value of 6.67 into 10 to the power of 11 Newton meter square kg square. Now, the mass of Earth is represented by me, which is also the constant, and the h is constant angular momentum that has been gained by the aircraft, whereas e or this epsilon will be the eccentricity of the orbit. Now, based on this eccentricity, we will be having different types of orbit. Eccentricity defines the shape of the orbit. For an ellipse, it is a ratio of the distance between the foci and the length of the major axis. Whereas, For example, in order to define an eccentricity, what happens? It will be a ratio of distance between the two foci, which is AB, to the length of the major axis, 1, 2, right? This proportion will define the eccentricity. And for a circle, it is both the foci will coincide, similar to your center circle, and it will be a constant radius. So the eccentricity particularly equals to 0. Now, and to understand how the orbit varies with the initial velocity of the spacecraft, the angular momentum and the eccentricity have been expressed in terms of useful parameters, where h equals to mrv as well as epsilon, which is nothing but your eccentricity, by rearranging the equation that we have got, orbital equation. Now, h, which is nothing but your angular momentum, which is constant throughout the orbit, it can be evaluated at the most convenient point where the radius is minimum and we know the velocity of the rocket. And with just initial velocity given to the spacecraft by the rocket and having fixed values for initial radius and velocity, we can see that both the angular momentum and the eccentricity are fixed. Thus, the shape of the orbit depends only on the initial velocity, that is V0, and the distance from the center of the Earth. Now, orbits, these are some orbit shapes with differing eccentricity. Now, a circular orbit with eccentricity value as 0. Now, elliptical orbit will be ranging from, sorry, just a second. Elliptical value, epsilon will be ranging from 0 to 1, right? And now what has been shown in the figure, elliptical orbit is having an eccentricity of 0.65, whereas a parabolic orbit, which doesn't have any end, right? One end will be having where eccentricity is greater than 1. Now, any for larger eccentricities for a shape, the orbit becomes hyperbola, where it is more open than the parabola. Right? Now, among these, there is a few terminology that everyone is supposed to know. Apogee, perigee. In any elliptical orbit, we will be having two terms, particularly apogee and perigee. Whereas apogee is the maximum point in an orbit away from the Earth. Let's say not from any celestial body. Let's say this is an Earth, right? If you are considering a circular orbit, apogee and perigee both are same, right? It means the distance in both ways it is same. Whereas coming for your elliptical orbit, you will be having apogee, which is the highest point from the center of the Earth, and the lowest point along the orbit towards the celestial body or towards the Earth will be your perigee, right? Based on the distancing between these two, you can determine the time through which an object orbits around the Earth. Now, this maximum and minimum, coming for your parabolic and hyperbolic, you will be having perigee and no apogee because due to the high eccentric rates. Now, as we discussed earlier, we know we will be having initial radius or initial velocity and distance, which is r0 and v0. By putting onto your this equation. What will be getting? We will be getting an eccentric value in this form. Now, we know that for eccentricity equals to 0, particularly for circular orbits, the initial radius as well as the velocity is equals to your component mass as well as gravitational constant. Now, by rearranging this term, what we can do, we can find out the initial velocity that is required from the center of the earth to maintain that orbit, right? Particularly circular. It means, let me reiterate, for a circular orbit, V0 will be initial velocity that is required from the center of earth to maintain an altitude of h0 or particularly r0 with eccentricity as 0. Right? Now, in this case, a mass of the earth, which is already a constant, 5.975 into 1024. Sorry, 10 to the power. Let me just reiterate, 10 to the power of 24 kgs. And the mean radius for the earth is 6,371 kilometers. Therefore, any initial radius above 500 kilometers of earth, right? For example, if this is my earth and this is my earth radius, right, and anything above that up 500 kilometer, right, initial radius of 500 kilometers, so total radius will be your 6,871 kilometer, right? In order to maintain any object at an altitude of 6,871 kilometer, you require around 7.6 kilometer per second as the velocity for an object to maintain that altitude. If the velocity of the spacecraft is somewhat greater than the minimum value, so the eccentricity is little greater than 0. Somewhat greater than 0, but less than 1. Now, this defines what? The cos angle, cos theta, which is again infinite, and the radius and the velocity, which again depends on the location of the spacecraft. I mean, it is towards peri, apo, peri to apogee or apogee to peri. Now, in such elliptical orbit, the product of velocity and radius has to remain constant, so that the angular momentum has to be conserved. That means when the radius of Earth is smallest, at the closest approach of the Earth, which is at perigee, the velocity is greatest, whereas while as the radius increases, the velocity drops, and being the lowest point at the most distant point of the Earth, the energy decreases. Elliptical orbits can be very eccentric. The spacecraft in such orbits will travel outwards many Earth radii before returning to pass through the injection point. And elliptical orbits are most important because they are used to transfer spacecraft from one circular orbit to other circular orbit. Let us discuss this a bit. Right? This is one of your foci in which Earth is being located, and this is your spacecraft. Let me just understand. And this is your perigee, and this is your apogee. Now, Earth will try to pull together because of its own gravitational field, and being an elliptical orbit, what happens at the perigee, the orbit will be moving toward perigee to apogee and apogee to apogee. Now, here, due to its height from the Earth or the radius from the Earth, what happens is you can easily maintain the potential energy, right? Particularly at that point, you will be having higher kinetic energy and lower potential energy. Now, As soon as the object or particular spacecraft moves from perigee to apogee, what happens, which is the farthest distance in terms, your h value, particularly height, increases, right? Which also, in a simple form, potential energy increases and kinetic energy decreases at apogee. Now again, from apogee to perigee, you are reducing your height. So from A to P, potential decreases and kinetic energies. So in what we can understand among this is basically towards your apogee, the velocity decreases, whereas towards the perigee, your velocity increases, right? Now, why these are used? Particularly in order to transfer orbits, particularly transfer an object from lower Earth to upper circular orbits, right? These eccentric or elliptical orbits are primarily used in or as a media or as a path which can be calculated to transfer or to move objects from lower altitudes to higher altitudes. Now, as the velocity is given to spacecraft increases, the eccentricity of orbit becomes greater and the apogee will move farther out, right, with the initial velocity. Now, as if we are increasing the velocity again at perigee, what happens? The apogee point will move farther out from the Earth. As the velocity increases at the perigee, the ellipse will become more wider and finally becoming a parabola or at least a hyperbola, escaping the Earth's gravitational wave. Now, the orbit ceases to be closed and the spacecraft never returns. In geometric term, the ellipse has been converted into a parabola and has a property of the trajectory become parallel to the axis at infinity. To be frank, the spacecraft will be parallelly moving along with the Earth. Now, from the expressions, particularly previous expressions, what we can see, if we are putting eccentricity as 1 with your initial value, these are the forms we will be getting. And with the initial velocity that is needed for an eccentric orbit, this will be your 2gm mass of Earth divided by r0 with the initial. And this is the escape velocity, the minimum velocity that is must be given for a spacecraft to escape from the Earth's gravitational field. Now, there are two notable points regarding the escape trajectories. The first is the velocity necessary to escape is just 2 or 1.4 times the velocity that is required to remain in low Earth orbit. For example, let's say on Earth, if you are sending an object right from Earth to escape the Earth's gravitational field, now at this time you require more energy to send it out. So what if, in order to escape the gravitational wave, first you are parking your orbit around the Earth at certain altitude which has its own energy to be maintained. Next, you are adding up certain amount of velocity further to escape, right? Now this require only the twice or 1.41 types of the velocity that has been required to maintain at low Earth orbit. Now, and the second point is, to escape from Earth, the initial direction of travel should be parallel to the Earth's surface, not the perpendicular, right? Let's say if this is my Earth, in order to escape the Earth's gravitational field, the orbital path should be parallel to the Earth rather than being perpendicular, right? Next, there are few equations in which the velocity of the tangential and circular orbits are there. As we had derived earlier, initial velocity for a circular orbit And the escape velocity for a parabolic orbit, it means to escape Earth's gravitational field. And for elliptical orbits, this should be the velocity ratio that is being maintained. Now, R0 as defined in elliptical orbits as well as any other orbits is the perigee radius, is the least amount of height, right? The height, particularly from the center of the Earth, at which the orbit is in Earth. Next, R2 will be with respect to the apogee from the center of the Earth, and V1 will be the elliptical velocity, particularly the velocity available at the perigee, and the V2 will be with respect to apogee. Right? Now, let us understand in what way the orbital altitude as well as the injection velocity varies. Now, as we have discussed, for any object to get an escape velocity, these are the orbital altitudes, and this will be a injection velocity in which we are supposed to move. Now, as soon as you are increasing your orbital altitude in terms of the kilometer or your final altitude, the injection velocity decreases. Why? Because for a circular object, if we are considering for first, let's say, circular object rather than elliptical orbit, the escape velocity for the same curve, let's say we are going for 10,000 kilometer, altitude, right? The velocity that is needed for a circular object in order to maintain an altitude of 10,000 kilometers on the Earth, particularly from the center, is minimal, around 4,000 to 5,000 meter per second, whereas for an elliptical orbit is bit more higher, around 6,000. Right? Now, if you are going in order to escape the Earth's velocity, particularly gravitational field, right? In order to maintain the gravitational field, what we require is more amount of energy or more amount of injection velocity to directly escape. So, as previously informed, in order to get 8,000 approximately, not 8,000, around 7,000 meter per second of velocity from the start is hard, because you will be requiring more amount of propellant and more amount of energy to be created to maintain this velocity. Rather than what we can do, basically, we can directly inject our satellite to either any one of the circular or an elliptical orbit, then increase its escape velocity or increase its velocity to a certain point where it can escape. Right? For example, let's say we are creating an initial velocity of 5,000 meter per second circular orbit. Right? Upon circular, we are increasing its altitude to somewhere around 7,000 meter per second to escape. Right? Rather than changing my velocity from 0 to 5,000, 0 to 7,000 directly, it is better as well as convenient for me to transfer my object to a first circular, then and escape the Earth's gravitational field. Right? In the next class, we will be discussing regarding the orbital transfer trajectories as well as multi-staging of rockets. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.